Hello AP Physics 1 students. You're going to watch this video after watching the video that Mr. Rosenwald produced going through the solutions for problems 9 and 10. I just have some things I want to add to it. Also, my notation is just a little bit different from the way he writes things. I just want to be consistent, okay? So first of all, he writes V for voltage. I'd like you to write delta V. And so, for example, the first thing, one of the things you want to find is the total current. So I would write it as I total. IT is fine as well, the way Mr. Rosenwald did. But I want you to write it as delta VB over REQ. It's just a matter of different notation. You're going to see this throughout your science career. Different teachers, different textbooks use different notation. But in our class, I want us to use delta V to remind us that voltage is the same thing as potential difference. So this delta VB, the battery voltage divided by REQ, that got you the total current for the circuit. By a similar token, when you want to write Ohm's law to find the individual voltages, you can write delta V1 equals I1 R1, delta V2 equals I2 R2. And so I just want you to go back and maybe put all those deltas in case you were writing it the same way Mr. Rosenwald was. But just difference in notation. And then when it comes to calculating the power, for all the power calculations, Mr. Rosenwald was using I delta V, but I want to validate the fact that, of course, you could use other equations as well. So, for example, when you're finding the power in resistor 1, if you wanted to do I squared R, you would just write it as P1 equals I1 squared R1. Or if you wanted to use delta V squared over R, P1 would be delta V1 squared over R1. Again, use the delta V notation and make sure you're using subscripts for everything. Notice every single time I write any of these equations for Ohm's law, for the power equation, I'm using subscripts, so we really know exactly which terms we're using to link things together. One of the last things to do in problems 9 and 10 is to draw on the circuit. I'm a huge proponent of this. It's a very visual sort of thing, especially when this is a very abstract idea. And so we really want to go back and make sure we're labeling the circuit diagram with as much as possible. So, for example, one of the first things we found in problem 9 was the total current. That's the 0.6 amps. We established the idea that the total current is all the charges flowing, in this case through the battery. So I like to label it right there on the circuit coming out of the positive terminal of the battery, represented by the long line. And so I draw a little arrow here showing that all 0.6 amps comes out of the battery. Here's total current. Now, just like I first talked about with current, remember, current is a scalar quantity, and yet we are drawing an arrow here. It's more like sort of like the velocity vector for the charges, and yet we're labeling it with a current, which I know is totally wrong, but we're going to do it anyway. It helps us visualize which way the charges are flowing around. And so here all the charges are coming out of the battery. That's the 0.6 amps. Since there's only one path to get around, that means that all these charges have to go through resistor 1. So here we're going to label that 0.6 amps also flows through resistor 1. There's no junctions here, and so all the charges are going to flow through resistor 2 as well. And so this is a very visual reminder that with only one path around the series connection, all the charges that come out of the battery flow through resistor 1 as well as flow through resistor 2. There's no choices to be made. There's nowhere else for these charges to go. You also want to be labeling the voltages. And so we calculated 2.4 volts for the 4 ohm resistor and 3.6 volts for the 6 ohm resistor. Label them right there on the circuit. Again, it's a very visual reminder showing us that the voltage across the battery is then split among these voltages here across the individual resistors. I also like to go back to the ski resort analogy. We're watching the charges go up and down the mountain, and the battery represents the ski lift. I always like to start here at the negative terminal. Where is that on the mountain? That's the lowest potential, so that's going to be the bottom of the mountain, right? So an individual charge gets on the ski lift, takes the ski lift to the top of the mountain, gaining 6 volts, or going up 600 meters, however you want to visualize it, but there they are at the top of the mountain. That's the positive terminal. They're released onto the slope, and by going through the resistor, where are they going on the mountain? Well, they're losing voltage. That's the job of a resistor, is to release energy. Energy per charge is voltage, right? So it's coming down the mountain 2.4 volts every 240 meters. And notice that it's certainly not back at start, right? The only place to pick up the ski lift is at the negative terminal, and the skier is not there. And so there's more to do. So by dropping 2.4 volts, it hasn't finished yet. It continues around the circuit, drops the remaining 3.6 volts for a total drop of 3.6 volts, of 6 volts, which makes sense. It gained 6 volts by going through the battery, lost 2.4 here, lost 3.6 here. And this is a very visual way of seeing that whatever it gains by going through the battery, it has to drop by going through the resistors. Gain 6 volts, lose a total of 6 volts by going around the circuit. And so for the parallel circuit in problem 10, we can do the same thing. First thing is we found the total current, which we represent as coming out of the battery. So 2.5 amps comes out of the positive terminal of the battery, and then it gets to the junction. It's got to split up. The next thing you did was you found the voltages. And remember, in parallel, of course, the voltages are the same, so immediately you can write 6 volts for each of these resistors. It's a very visual thing. Any charge that gains 6 volts by going through the battery must lose 6 volts by going through this resistor, or taking the other path across the junction there, lose 6 volts by going through that resistor. And so it's a very visual thing, tracking the flow of any individual charge as it goes around the circuit. Notice I'm also writing the 6 volts over the 4 ohms, and 6 volts over the 6 ohms. Here again, I wrote the voltage over the resistance, voltage over the resistance. This is really just a visual reminder that if you're going to find the current, it's voltage over resistance to find the current. You then want to label the individual currents. Here's 1.5 amps going through this resistor, 1.00 amps going through this resistor, and it's a very visual sort of thing. Charges go through here, all the 2.5 amps goes here. At the junction, the charges split up. Some go down this path, and some go down this path to add back up at this junction to form the 2.50 amps. Labeling the circuit also provides you with a way to visualize what happens when things go wrong. So let's say, for example, you're looking at the series circuit and you get a little confused. Maybe you don't have your notes in front of you and you say, in series, all the voltages are the same. So let's say if there's 6 volts across the battery, there's 6 volts here and 6 volts there. Well, let's visualize this with the ski resort analogy and think what could be going wrong here, right? So let's imagine a charge that goes through the battery, which is going through across the ski lift, going to the top of the mountain, gains 6 volts. And then it goes to this resistor, which means it's dropping 6 volts, and then goes to this resistor and drops another 6 volts. So let's visualize that. Here the charge went up 6 and came down a total of 12. Well, that means on the mountain it would go up 600 meters and come down a total of 1,200 meters. And so you say to yourself, wait a second, where is this skier who went up 600 and came down 1,200? Well, then that means the skier is underground, and that doesn't make any sense. And that provides you with a very visual reminder that it doesn't make any sense to gain 6 volts to the battery and then lose a total of 12 volts through the circuit, which means that it didn't make sense. You must have done something wrong. By the same token, let's imagine you're doing the parallel circuit and you get a little confused and you think, all the currents are the same. There's 2.5 amps here, there's 2.5 amps through either of these resistors. Let's visualize this one as well. Now, we can't have 2.5 skiers, so imagine it's 25 skiers, all right? So 25 skiers go up the ski lift to the top of the mountain, and here's the junction. And this is saying that means 25 skiers come down this path at the same time. The 25 skiers go down this path. And so we have 25 skiers going up the mountain, a total of 50 skiers coming down the mountain. You say to yourself, what does that mean? Where do these extra skiers come from? That doesn't make any sense. And so if you draw on the circuit and then you think about the ski resort analogy and you get to some result that doesn't make any sense, you did something wrong. And so here we see, of course, if 25 skiers go up the mountain, 15 skiers come down this path, and 10 skiers come down this path. That makes sense. 25 skiers go up, 25 skiers come down. Fantastic. At this point, if you haven't yet downloaded and printed the notes page comparing series and parallel combinations, go ahead and do that. Pause the video while you do so, and then come back. Okay, so here we have a notes page very similar to how we compared series and parallel capacitors. You want to have problems 9 and 10 in front of you as you go through this. In a series connection, there's only one path. They depend on each other. And here, this last part is really the strongest way to know which resistors are in series. If it goes through one, then the charge must go through the next. That's a series connection. It won't always look like the ones we've drawn so far, but this last part here is the strongest way of knowing if resistors are in series. But for parallel, of course, there's multiple paths. We'll see a junction on the circuit diagram. They're also each independent of the others. If you take one resistor out, the other one still functions. You saw this with the light bulb circuits when you did it in the simulation. What are the consequences of this? Well, in series, when there's only one path, the currents have to be the same. There's nowhere else for the charges to go. But in parallel, of course, when there's a junction, the charges split up at the junction. The current splits up. What are the consequences of that? Well, since each resistor is on its own path and independent, the voltages must be the same. That's seen here in problem 10, where there's only one resistor on each path, and so each one drops the total battery voltage. That's not going to necessarily be the same for all circuits. Maybe there'll be multiple resistors on a path, but still, the voltages on any path must be the same. But in series, with only one path, the voltage has to split up. That's what we showed, right? No individual resistor can drop all the voltage. It's split among the individual resistors, so they add back up to the battery voltage. We see in the problem 9, when we put more resistors there in parallel, in series, they add up to make a larger equivalent resistance. In parallel, however, the individual resistors are larger than the total, so the total resistance actually drops with the circuit. Now, why does this happen? Well, if we go back to our ski resort analogy, let's say you're the owner of the ski resort, and at the start of the business day, there's not a whole lot of skiers there, so you only have one slope open. Then more people come, and so you open maybe a second slope. But now you only have the two slopes open, and more people are coming, and so the crowds are getting larger, the lines are getting longer. What can you do? Well, as the owner of the ski resort, you can open more trails. The more trails you open, the more skiers can move. As a result, the total current increases, which means that the overall resistance decreased. Mathematically, it's showing the equation, but in our analogy, this is what's happening. The more paths there are, the more choices there are, and so the overall resistance drops. Now let's compare the total power. So look at problems 9 and 10 and see through which combination of resistors did more power get generated, did more power get dissipated. So hopefully you see that in the series there's in general less power dissipated, and so since power translates to brightness for light bulbs would generally be dimmer. For parallel, there's more power dissipated. Light bulbs are brighter. Look at the individual light bulbs, the individual resistors. It's the same resistors in problems 9 and 10 in series or parallel. Look at the individual powers generated. You should see there's a lot less power in the series connection, a lot more power in the parallel connection. They're brighter in parallel, they're dimmer in series. So what are the consequences of this? Well, what would be the advantage to putting these light bulbs, let's say, in a parallel connection? Of course the advantage is they're brighter, right? They're giving off more energy per time. That's great. But what's the disadvantage? Well, if you look at the power generated by the battery, it's giving off more energy per time. This battery is going to run out more quickly, or if you're plugged into the wall, you'll be using up energy at a faster rate. You're paying more money for every monthly bill. So it's a trade-off. So what is the advantage to putting them in series? Well, you're using the energy at a slower rate. You're paying less money per time. What's the disadvantage? Well, these light bulbs are now dimmer. However, sometimes that's not a disadvantage. You probably have some sort of electrical component at home, maybe a TV or a DVD player, so that when you press the power button, a little light comes on letting you know it's functioning. That light is coming on to let you know all the components inside the same device are functioning together. What sort of connection is that? Well, that's going to be a series connection. The light comes on at the same time all the other components. Now, you're probably not using that light to illuminate the room or read something by, right? And so it doesn't have to be very bright. So it's okay that they're in series, that light is kind of dim, as long as it's just telling you things are functioning. What about the wiring in your house? Are the outlets in series or parallel? Hopefully you realize they have to be in parallel. Why would you know that? Well, if in series all the resistors depend on each other, that would mean that if you're downstairs watching TV and someone upstairs turns off a light switch, well, that would mean your TV would go off if everything's in series. That would also mean for one thing to be on, everything in the house would have to be on. That's a complete waste of money. And so from outlet to outlet, they're wired in parallel. Now you probably have somewhere in your house where you turn a light switch on and something else comes on. Maybe a fan comes on or another light goes on at the same time. What sort of connection is that? Well, that's going to be series. And so maybe for an individual outlet, some things are wired in series, but from outlet to outlet, they're wired in parallel. Now at this point, I want you to dig up your chart that looks like this that also involves capacitors, and we're going to make a comparison. Here they are side by side, just in case you couldn't find yours. And now that you see them side by side, you should see some connections. For example, here's everything in parallel. Parallel resistors, parallel capacitors, and look what happens here. The voltages are the same no matter what. Well, that's just a matter of charges having to be along an equal potential. Here, the current splits. Here, the charges split and add up. Well, remember, current just tracks the flow of charge, and so really that's the same idea. Charges don't flow through a capacitor, but they settle in on the capacitors and they add back up to the total charge that went through the battery. Here, the charges split up, the current split up to the total current that went through the battery. And look at this. Even this is the same idea, where power is really just the rate of energy being produced. So there's more power in resistors in parallel, more energy stored. Let's look at the series. Here again, we see everything sort of the same. The currents are the same in series, the charge are the same in series. The voltage splits in series, the voltage is split among the series capacitors, and look at this. Even the power and energy is the same idea. Less energy per time, less energy stored. And so we see that, yes, of course, they're not the same devices. They play very similar roles in terms of all these terms.